Hello, this is my project 3 for Calc 3. So let us start off with solid. As you can see here, I have my three-dimensional shape. I have a vertice centered on the origin, which is of course 0, 0, 0. I decided that the best coordinate system to use here was the Cartesian coordinate system. That is because all of the boundaries of the box are on the flat planes and they align perfectly with x, y, and z axes, meaning that my limits of integration are all constants from 0 to a, 0 to b, 0 to c. And if I try to use cylindrical or spherical coordinates, the limits would turn into incredibly messy trigonometric functions. That's part A. Let me get the second point. All right, going on to the volume. Just need to set up an integral with 1 as the integrand, which you can see right there. And then I integrate with respect to, start off with, on the inside, integrating with respect to z, as you can see here, 1, z. Then I get c, from 0 to c, I get c. Then I integrate with respect to y, which is, start off with the c dy, and my output is, from 0 to b, I get b times c. That's my output. Because obviously when you multiply it by the 0, you cancel out the, it just all becomes 0. Then from respect to x, I get bc dx. And then, of course, if you can't see that, sorry, it's a very terribly, poorly written a. But from 0 to a, you get a times b times c. So the volume is a times b times c. And then to compute the mass, rather than using integrating 1, we integrate. Sorry, I have a lot in my room. We integrate via the density function, which is f of x, y, z equals e to the z, or e to the negative z. And so, of course, we start off the same way we did with the volume, but instead we're integrating with e to the z. With respect to z, you wind up with e to the negative c minus e to the 0, which is obviously going to be 1, so you get 1 minus e to the c. And we still follow the same pattern here, where we bring this down, integrate it from 0 to b. That gives us, with respect to y, minus 1e over to the negative c power. And then we just, that allows us to multiply the whole function by b, bring that down, and kind of same repetition here, same pattern, and then we get ab times 1 minus e to the negative c, and that gives us our entire mass. And then the final portion of this this part, or part 1, is to find the centroid coordinates, not the center of mass, but the geometric coordinates. So basically, we're just going to find the average of each specific. We're trying to calculate like the center of each and every single line. And basically, of course, we're going to know that we're going to wind up with about like half of wherever half of A is, half of B is, half of C is. But just to kind of prove that, I'll do it with the first one and then basically explain why I did it the same as the other ones. We start with this equation where we take, sorry, we'll use the volume we'll divide by the volume, and we'll calculate the x average by doing the integral of from 0 to a, 0 to b, 0 to c. Of course, I evaluated it here. X dx. Oh, I forgot to write a 1 here. 1 second. Okay, back to explaining. When I am evaluating from x average, or that's what I'm looking for, I set a as x dx, and everything else integrating with I'm integrating 1. And so that gives you x squared over 2 from 0 to a times b times c, which gives me a squared times b times c divided by 2. Then you divide it by the volume, which I kind of left back over here. But I divide by the volume, which we already know is ABC from our previous part A, and that gives you A over 2. When you go and evaluate from Y and Z, you actually just, for Y, you change the 1 out for Y and change the X out for 1, which winds up giving you B over 2. And for Z, you switch out the X out for 1, leave the Y as 1, and then this would be Z, and that gives you C over 2. And so to get your final answer, the centroid is at where we thought it was. It's going to be A divided by 2, B divided by 2, and C divided by 2. Yeah. All right, on to the next part. All right, here's part 2 for project. This is our semicircular plate. It's with Y is greater than or equal to 0 with radius A. And there's a tiny uniform thickness denoted by the change in Z, as you can see right here. Yeah, the density of the material increases as you move up the y-axis. The best coordinate system to use here is cylindrical coordinates because it's a circular boundary. X squared plus y squared equals a squared. Cartesian coordinates wouldn't work well here just because it create like a square root limit, like y equals, square root of a minus x squared. So yeah, it just works exactly like 2D polar coordinates, and then you just add on the z-axis. So we get beautiful constants looking like radius r is 0 is from 0 to r to a, or less than or equal to 0. Greater than or equal to 0, less than or equal to a. The theta is less than or equal to is greater than or equal to 0, or and less than or equal to pi. And height is less than or equal to z. Greater than or equal to z. Sorry, I have to get that right. And less than or equal to change in z. To compute volume, we start off with our semicircular area because volume equals base times height. So start with a semicircular area, which is 1/2 times pi times a, because that's our radius squared. 1/2 1/2 pi r squared, because this is a semicircle, so that's why I multiplied by 1/2. And then our height would be the change in z. So yeah, disregard this portion. Let us go to the mass. Sorry, I winded up using Sharpie for the last one. Bad idea. So it was very hard for me to erase. Now it should be easier to erase. Anyway, the mass requires to integrate the density function. So dropping, you take the triple integral of our density equation, which since we're using cylindrical coordinates, our density f of x and y equals y is actually y equals r sine of theta. Of course, we implement our Jacobian r in our derivations. So yeah, I actually didn't write the way we would start it out, but it's basically m equals the integral of from 0 to pi, which is the integral of 0 to a, which is the integral of 0 to change in z of r sine theta. R squared sine theta times r times dz times dr theta. I actually think I put that there. But anyway, with respect to z, we start off taking our integral for that, which I went in. Sorry, one second. Now I remember what I did. Since there are no actual Yeah. Since there are no z variables in r squared sine of theta, we actually just multiply the whole thing by z, which is why I have that here. When you go to respect to theta, you get for the integral from 0 to pi theta d theta fleshes out to negative cosine from 0 to pi, and then that just really simplifies nicely to 2. And then when you do it with respect to the radius r, you get r squared of dr. Of course, goes to r to the third over 3. A from 0 to a is a to the third over 3, because the 0 cancels out, of course. And then what I did was just I multiplied all of those terms. So you get 2/3 a over a to times a to the third times change in z, and yeah, that's the answer for the mass. And then when you want to do centroid coordinates, what you do is you you need to calculate. I mean, you divide it up, which so the you don't need to really do calculus for the x average because it's perfectly symmetric across the y-axis. So the average of x is 0. So however far x spans, it's going to be at the dead center of the origin. So and then when you want to find y, you you realize that's the exact same integral we evaluated for mass. Since that's the number we evaluated for mass, I just divided what I evaluated for mass by volume to get that centroid value, which when simplified, you cancel the z terms, you get 4a over 3 pi. And then on to the final part, the z average, it's literally just the height of the it's the height of the change in z divided by 2. So it's just halfway up, so you divide change in z by 2, which gives us the final coordinate z, or x being 0, y being 4a over 3 pi, and z being change in z over 2. All right, here's part 3 of project 3, the solid of a revolution. As you can see, we're taking a 2D line, z equals a minus x, where x is greater than or equal to 0, sweeping at 360 degrees, and it creates a circular cone with a base of radius a, and a height of a. The best coordinate system here to use here is cylindrical. It's basically the standard for revolving around any axis. The distance from the z-axis of that line would be a radius r, and so 0 is less than, or r is greater than or equal to 0, but it's also less than or equal to a. And that gives us our radius, that gives us our sweep, which is becomes our angle, which is from 0 to theta to 2 pi, or theta being greater than or equal to 0 and less than or equal to 2 pi. The height of this function is from greater than or equal to 0 or less than or equal for a minus r, since x becomes r. You travel down the cone. Let's go to computing the volume. It's a triple integral using 1 as the integrand, including the Jacobian multiplier r, integrating from respect to z. I did it right down here in small writing because I was running out of room. Speaking of which, I'm going to wind up pausing and erasing all this so I can show the centroid coordinates. But start off r dz, simplified or integrated, r times z, which winds up becoming r times a minus r, but then you multiply it inside, you get ar minus r squared. Then I brought the ar down here to become to integrate with respect to r. That's from 0 to a r minus r squared, ar squared over 2, r cubed over minus r cubed over 3, evaluated over from 0 to a gives you, simplifies to a cubed over 6. Then you bring that up to integrating with respect to theta. That gives you from 0 to 2 pi. Simplifies pretty nicely, and you get pi times a cubed over 3, and that perfectly matches of the volume equation of 1/3 times pi times the radius. But yeah, let's go over to mass. Mass was really, really messy. I apologize in advance. But yeah, let's begin. So we start off with the density equation. We wanted to convert that to cylindrical. So that is, if you cannot read it properly, which I don't blame you, that would be a squared minus r squared minus z squared. Put that into mass, and start off by evaluating at z. That part's not too bad. You just you evaluate with respect to z, as you can see I did here. Then I wound up substituting z equals substituting z with a minus r, gives us r times a squared minus r squared times a minus r over a minus r cubed, all of that over 3. And then you factor out an r times a minus r to simplify the algebra, which is what I did right there. And then you get, it was a massive algebraic expansion, so I really kind of just simplified it to 2/3 times a cubed times r minus 3ar cubed plus 2r to the 4th power. And then we integrate with respect to r. That just involves taking our previous equation, plugging it into this integral, 2/3, integrated from 0 to a with our ar cubed. Actually, since you can read that, I'm just going to go on with showing the rest of this. This portion's a little messy, but I wanted to evaluating it from 0 to a, and that brought it back over here. That gave us 2/3 a to the 5th times 1/2 minus 3/4 plus 2/5, which that is a terrible written 5. But anyway, that winds up simplifying pretty nicely to a to the 5th power. Bring that a to the 5th power to the integrating from respect to theta. This one simplifies pretty nicely. We get pi times a to the 5th over 5. And then I'm just going to pause it here so I can show my centroid computation, or sorry, my centroid computing. Okay, we are back with the centroid coordinates. So to start off, we just need to find the geometric center of each portion. So the beautiful part about this problem, which I hate the fact that there's glare, but x and y are both 0, because when you revolve the shape 360 degrees around the x-axis, the mass is actually distributed perfectly symmetrically around that axis. So you can set those equal to 0. So all we need to do is find the z average, which of course is 1 over volume triple integral of z dv, which is fleshed out here. Of course, and I just pan through this math real quick to show what I did. Get these last bits, but wind up getting a nice simplified average of a over 4 after we divide by v, which was found in the previous part 2 actually, which is pi equals a cubed over 3. So once we divide that, we get a nice a over 4, which gives us our centroid, which is 0, 0, a over 4. Yeah. Thank you. On to the next. All right, here is part 4.3. This is our solid pyramid. This is where the base is bounded by absolute value of x plus the absolute value of y is less than or equal to 1, which creates this like diamond shape at the very base, spanning from -1 to 1 on all both axes. The top boundary is z equals 1 minus absolute value of x minus the absolute value of y, peaking at the apex, which is 0, 0, 1. Best coordinate system to use here, I'd say, is the Cartesian rectangular coordinates, because all of the boundaries are flat angled planes. So yeah, integrating across the entire domain at once would create a very messy function. So instead, we're just going to try and use symmetry here. The pyramid is perfectly symmetrical across all 4 quadrants of the xy plane. So we'll just set up an integral strictly for the first octant, where x, y, and z are all positive, meaning the absolute values aren't necessary. Then multiply the resulting volume mass by integrals of 4, or mass integrals by 4. So that's what we did. Starting off here, as you can see, volume equals 4 times integral from 0 to 1, 0 to 1 minus x, 0 to 1 minus x minus y, of 1 dz, dy, dz. So we started off with respect to z, quick and simple. That gives us 1 minus x minus y. Then evaluate that, or integrate that with respect to y, gives us 1 minus x times y minus y squared over 2. And then evaluated, we bring expand that out, gives us, as you can see with the little I've done down here, expands out to 1 minus x squared over 2. Bring that down and integrate it with respect to x. This is where our multiple of 4 comes in, because at the very end, that's when we plug in that volume. But anyway, so we integrate it, evaluate it from 0 to 1. That gives us 2/3. And then, of course, but because we've already multiplied it, so yeah, it's just 2/3. Then let's go up to mass. Same deal here, multiplying it by 4, but instead we are using we're using a density of F equals 1 minus z. I'm sorry, that looks like a 2 right there, but that is actually a z. But to keep in mind, it approaches the pyramid density approaches 0 at the apex, but the bottom of the pyramid is dense. So that's why that is our mass equation. So let's start off with respect to z. Of course, when we take that integral, we get 1. We get 1 minus x minus y minus 1 minus x minus y squared over 2. Plug that into our y equation. Gives us. I'll just show the evaluation actually, because this wound up getting pretty messy. Still dealing with the issues from the Sharpie earlier. But yeah, we wound up simplifying that to 1 second. Okay, I'm back. When you evaluate the upper limit, it becomes 0, which because y equals 1 minus x, so both terms become 0. When you evaluate it at the lower limit, both terms remain 1 minus x. So in front of this, which you actually see this smudge erased for, is from 0 minus this. So this is actually this whole function is actually negative. So let me fix that, because these two wind up simplifying out to be, this becomes a positive, this becomes a negative. I'm going to make that, oh, I used Sharpie. Good gracious, that's going to be a pain to get out later. But this is the last part, so it doesn't matter that much. So, and then we go down, integrate that with respect to x. Sorry, trying to put a cap back on. Flush all of that out, evaluate it from 0 to 1. That one's really messy because I started running out of room. But once you evaluate it from 0 to 1, you get basically 4 times 4 over 24 minus 1 over 24 equals 1/2. And that is that's our mass. Now to compute the centroid coordinates, this one's another beautiful one because x and y average are both 0 because of the perfect radial symmetry across the xz and yz planes. So we will only be doing the z average, of course. So start it off right here. Flush it down to here. Got to, I expanded it, dropped in the 1 minus x minus y squared, all of that over 2. And right down here. Then I multiplied the 4 times the integral from 0 to 1 of that. Hold on 1 second. All right, I figured out what looked weird. So this is actually supposed to be to the 3rd power right here, and that is the 2 from this. This is the problem with having a lack of space. But yeah, bringing it to the 3rd power, and then all of that is actually supposed to be over 6. So let me get the real marker real fast and draw that 6 in. So all of that over 6, back and finishing all this. But yeah, we get 4 times the integral from 0 to 1 over 1 minus x to the 3rd over 6. And then we evaluate all of that. You bring the 6 out. And, gosh, this looks terribly messy. But negative 1 minus x to the 4th over 4, evaluated from 1 to 0, equals 2/3 times 1/4 equals 1/6. That's our, so we take that z average, divide that by our volume, which is 2/3, and then we get 1/4. So whereas x and y are both 0, so our coordinates are 0, 0, and then our z coordinate is 1/4, giving us the centroid. All right.